Hi, my name is Chuck Taylor. I'm the Director of Flight Operations for Kitty Hawk and the Heaviside project. Heaviside is a remotely piloted single-seat eVTOL aircraft designed to be an air taxi service in the near future. So the configuration of the aircraft is a forward-swept wing, a traditional tail and canard, supported by 8 trailing edge motors, 4 in each half of the aircraft, that tilt as we transition from vertical flight to forward flight. So the motors are a typical brushless motor supported by variable pitch propellers. That pitch is linked to the tilt of the motor. So as we move from hover to the cruise configuration, the pitch of the propeller will increase to optimize for cruise flight and efficiency and noise. Since the first flight about 4 years ago, Heaviside 2 has evolved a little bit. We have been iterating on developing new propulsion systems, new propeller designs, and flight control systems to support the aircraft. But overall, the aircraft plan form and design has remained the same and has provided an excellent R&D tool to test out all these new technologies that will eventually lead to a product level aircraft. Yeah, so one surprising aspect is Heaviside 2 is probably a little smaller than most people expect. It is a single seat aircraft. It is quite compact with a 23-foot wingspan, extremely light with a maximum takeoff weight of under 900 pounds with a person on board, and has a demonstrated range of up to 100 miles depending on its mission. The fuselage is about 18 feet long. Yeah, so Heaviside takes off and lands vertically and transitions to forward flight. It does not support conventional takeoff and landing. In addition to the 8 motors, we have traditional control surfaces like ailerons, elevators, and rudders on the tail. And the flight control system uses the combination of motors and control surfaces at any given time to control the aircraft. So what is unique about Heaviside is it is remotely piloted, meaning the pilot is not on board the aircraft. So it's operated very similar to small drones that people see in the consumer space. And it's been a revolutionary way to approach flight testing because we can accelerate our flight test schedule by mitigating risk to any humans during that portion of development. So we can go out and test this aircraft, push the aircraft harder and faster than you would in a traditional onboard piloted aircraft because there's no risk to human life. The emphasis is always the expansion of the envelope of the aircraft. You can incrementally approach that process by starting with simple hover flights, then moving on to transition where it's a bit of a vertical flight, it's a bit of forward flight, and then finally all the way to cruise flight. But within each one of those regimes, you have to demonstrate the aircraft is capable of tolerating high winds, maybe a loss of a motor or of a control surface in different failure modes. And we can accelerate that testing by not having that person on board, which dramatically reduces the risk level of any given test flight. In the early days that led to the development of this aircraft, our group was developing all sorts of new crazy flying contraptions on almost a monthly basis, trying out different configurations on a subscale level using simple things like carbon fiber tubes and blocks of foam, and allowed us to quickly iterate and look at each design outside of just simulation to prove whether or not it was going to be viable. So before Heaviside 2 existed, there was a Heaviside 1, and it was built using all carbon fiber tubes, foam, and a mixture of different composites and build methods. It was full scale, but half weight, and allowed us to prove this was a configuration that was going to be viable and was going to work well. It required very little infrastructure, and the small, lightweight nature of the aircraft lended itself to being a very simple operation. So there's a trailer located off camera here, simple trailer. The whole aircraft within 30 minutes packs up, fits into that trailer. That trailer plus a generator or some source of power is all that is needed to flight test this aircraft. Our current flight test facilities outside of the town of Hollister is located out in some private pasture land away from an airport because we don't need traditional infrastructure that you tend to see with helicopters and fixed-wing airplanes. Flight testing has evolved from the early days of getting out there and testing whether or not the aircraft was even capable of flight. Now we've moved more into the stage of the refinement of the systems, iterating on individual components that we believe will eventually support a mass-scale certified flight operation. So one of the very interesting things we have coming up soon is actually our first human flight. So to date, all our flights have been without a person on board. And within the next few months, the first passenger will be getting on board this aircraft and going for a ride. in a remotely piloted eVTOL aircraft. Yeah, so the envelope of the aircraft contains many different things, whether that's tolerance to wind, its endurance, how the environment affects the aircraft, temperature, humidity, etc. And so when you start flight tests, you tend to constrain those variables as much as you can to the ideals so you can focus on early safe demonstration of flight. Then over the course of time, you incrementally open up each one of those until you've proven the aircraft meets its complete design envelope. So in the case of Heaviside 2, we have flown up to 180 miles an hour. We have flown over 100 nautical miles, and we have demonstrated failures of all major systems that are fully fault tolerant. So this aircraft is serial number 13. So we've built over 14 aircraft to date. We're continuing to build more. There's quite a few advantages to having the opportunity to build so many aircraft. It allows you to flex that manufacturing muscle, develop those processes to make these aircraft in an efficient and safe manner with great quality, but also allows us to accelerate flight testing by parallelizing efforts, having multiple teams flying at the same time. And each aircraft can be iterated on. We might modify one aircraft specifically for crash testing, for example, or another one we might try a new propulsion system. And having all those different aircraft allows us to stay flexible, agile, and moving quickly. So for me personally, this has been a dream come true. As a little kid, I grew up flying RC airplanes. Age 16, I jumped in a Cessna 172 and started on my pilot's license. From there, moved on and got into the world of drones over a decade ago, which has eventually brought me to this aircraft. So the team at Kitty Hawk is quite incredible. The eVTOL world is pretty small. All the different players in the space, especially in the Silicon Valley area, we're all great friends, and within our team is no different. It feels like a small family. It's a world-class group of engineers, technicians, and business people supporting the mission of getting out there and flying as often as we can. So over the next couple of years, we'll continue to use this aircraft as our development platform. The benefit of having so many flying aircraft and the ability to go out and fly on a almost daily basis is we can go test different operational type situations. So instead of waiting until we have a product aircraft and understanding how that integrates with the National Airspace System, we're working with partners like Agility Prime to go fly a fleet of these aircraft in Ohio using the SkyVision system, for example, which is a ground-based detect and avoid system. So being able to have a representative aircraft that will be very similar to our final product in that real-world environment has provided countless valuable learnings that you otherwise wouldn't get in a very sterilized test environment. Yeah, so one of the benefits of electric aircraft, and especially distributed electric propulsion, is we can reduce the sound profile of the aircraft, which is extremely important because anyone that's ever been near an airplane, even aviation enthusiasts, while it's awesome to see airplanes in the air, they are quite loud. If you can see an airplane, you're probably going to be able to hear it. And what's unique about Heaviside is at 1,000 feet away, you can't hear it. The lightest breeze will drown out the sound of the aircraft. And so that sound signature is very important from a product perspective, because you do not want these things near your neighborhood if they're going to be loud and noisy like a traditional helicopter. So the aircraft does sound a bit like a drone, just a bit scaled up, but that noise is only evident for a few seconds during takeoff and landing. We transition very quickly to forward flight, flying on the wings, where the propellers become almost inaudible. For the eVTOL industry to be successful and create this vision of a new transportation service available to all, we have to be able to manufacture these aircraft at a scale never seen before in the aviation industry. Potentially upwards of thousands of aircraft per year will have to be produced to meet that vision. That is hard to do with traditional methods of construction and manufacturing currently used in the aviation industry. So one of the big focuses at Kitty Hawk is how to make these aircraft as simple and as inexpensive as feasible to manufacture at scale. And while that number is important and extremely aggressive, that all plays into the cost per mile that the passenger would have to pay. Right now, if you look at a helicopter or even a car, a rideshare right now, you're paying upwards of a couple dollars per mile. If we want this to be truly a new type of transportation that people use on a daily basis, we need to get that price down cents per mile. And a lot of thought has to go into how to enable that vision. So while you may take some sacrifices in the efficiency of the aircraft and how it flies, you might be able to dramatically reduce the cost and subsequently the unit economics of that service.